I couldn't agree more. We have a fantastic group of speakers, or panelists here. It's really a dream team, and I am deeply privileged to get to ask them questions before anybody else does. Let's, I guess, give everybody a chance to get up here, and then I'll let everybody introduce themselves.
Hi everyone. Very exciting workshop so far. I've been active in Approximate Bayesian Inference for about 7 years now. Used basically everything there is under the sun. Started out with Monte Carlo methods, expectation propagation, and then I was one of the first to use variational inference with using what is now known as the reproduction trick. Last year, I should say, I'm also very active in GANs. Probably now most well known for my paper on improved techniques for training GANs. And I'm very excited to see lots of new work here, combining these different approaches to approximate Bayesian inference and really taking things to the next level.
Great, so I'm Zubin Garmani. I'm a bit of a dinosaur, I guess. Approximate inference. I've been very interested in variational methods for a long time. They've gone through many name changes over the years. Also I'm quite open-minded about my approximate inference methods, so I also have enjoyed playing around and developing MCMC methods and playing around with EP and variations on that and hybrids and all sorts of crazy things. Sequential Monte Carlo and so on. And one of the things I'll say is, sometimes I come into NIPS and think, there are no new ideas. It's all just rehashing stuff. But actually, at this workshop, I've just thought, wow, there are a lot of good ideas here. And I thought that we wouldn't be able to make much progress anymore, and that we milked all the approximate inference methods we could, but I actually think that the gradient is looking pretty good, and we're able to develop better and better, more efficient methods. So I'm pretty impressed with what's been going on. I'll say one other thing, which is that more recently I've been very interested in probabilistic programming, and part of the reason I'm interested in that is because I spent a youth painfully rederiving approximate inference methods for many, many different models, and I wouldn't want to have anybody else go through that. And so one thing to think about is, in the context of a lot of our new approximate inference methods, how general are they? Can we generalize them to a very broad class of models? Can we generalize them to, any computable probability distribution represented by a probabilistic program? And if we can, then that's super exciting, because then we can build tools that are really, really widely usable and disseminate these great ideas here.
Yeah, so I'm Max Welling. I'm in Amsterdam. I'm sort of half a dinosaur then, I guess. But I started out being very interested in belief propagation and mean field methods, and later also in MCMC methods, and in particularly how we can scale these models up to much larger data sets. And more recently, I've been more interested in combining all of that with deep learning. So can you combine probabilistic methods and graphical models with deep learning methods? And we've seen a lot of interesting results here today as well. And for me, it's sort of like a pendulum for me. So I start up, in one phase, a couple of years, I'm super excited about variational Bayes, and I think we'll solve the world, and we will do more flexible approximations, and this is the way to go. And then slowly, at some point, it swings the other way, and then I think, oh no, we should do MCMC sampling, and we can scale it up. And so at some point, it will sort of end up somewhere in the middle, maybe with some kind of combination. So happy to be here.
Hi, I'm Catherine Heller. I'm in the Duke University Statistics Department. I think a lot about applying approximate Bayesian inference methods to some of the different problems that I work on, including looking at different problems in medicine, like electronic health records data, where you might have a lot of health records, or big national databases, where you might have a lot of data coming in from mobile devices in the healthcare setting. I also do some work with social networks, right, where you have a large number of potential connections between, say, like people in a social network. How do you scale up inference so that you can make something sensible about how people are acting within a social network setting? And I've done a lot of thinking about how do you do inference in those particular settings. I've done a little bit of work combining Bayesian methods with deep learning, like Max just said. And I guess I should say that Zubin was my advisor, so I get to sit here and hope a little bit of what he knows rubbed off on me.
I'm Dave Bly at Columbia University. So Zubin's a dinosaur, and Max is half a dinosaur. I'm like a woolly mammoth. I've been working on variational methods for a lot of years. I learned about them basically from the papers of all the people up here, including Matt. I'm interested in applied large-scale Bayesian inference, which I think often or sometimes requires using variational methods. I'm interested in making them scalable and making them generic, kind of pointing to what Zubin said, so that they can apply to a large class of models, thinking about models where we can't even compute the likelihood, for example. And also interested in probabilistic programming for a lot of the reasons that Zubin mentioned.
Great, thanks everyone. So I guess some people talked about this a little bit already, but I'd like to just start things off by asking people to talk about applications. I'm sure we'll get into the sort of technical weeds, but I'd like to just get a sense of, we talk a lot about Bayesian inference and approximate inference and sort of uncertainty quantification and all that sort of thing. And we've also seen in the last 5 to 30 years enormous successes of machine learning that don't do any kind of real uncertainty quantification. And so I just like to get, anyone who wants to talk about kind of what are the applications where we really need to think about, where we really need to do inference in kind of the Bayesian sense, or some approximate Bayesian sense, as opposed to situations where just anything goes, and we just need to make some kind of prediction. What are the applications that really call out for that?
So I have an interesting story here. So I had a startup, Cypher, before it was acquired by Qualcomm. And we would work with Tata Steel, which was a company who was making steel, obviously. And it's like they have this steel plates like this, and they move under a sort of a battery of cameras. And so now and then there is defects on the steel, and you need to detect the defects and then classify them in 1 out of whatever 30 different classes. And so what we did is we didn't have enough labeled data, so we built an active learning loop. So in other words, you would make these pictures, and the system would be very uncertain about certain detections, and then they would send them to an expert, and then the expert would look at it on their phone, and they would sort of classify them, and then it would be sent back. But obviously, in order to do that well, you need some kind of uncertainty quantification about how well you think you can actually classify this particular example. And so there we used actually Yaron-Gulls and the Zubin-Garamanis method for MCMC dropout. It's a very simple extension of dropout to just get some reasonable uncertainty quantification on your predictions.
So I think this is a great question, the applications question. It sort of sometimes keeps me up at night, like I like being a Bayesian, but the world is sometimes, well, not looking at a room this big, but there's probably a room much bigger somewhere else where they're not Bayesian at all. And so why should we be Bayesian? And I think it's not for everything and not for everyone, but clearly situations where uncertainty matters. And again, just to echo what Max just said, for example, where uncertainty matters because your decision depends on uncertainty, like in active learning, that's a great example. Actually, if you look at all sort of RL that involves playing out futures, for example, in terms of like Monte Carlo tree search and things like that, there is certainty certainly matters for the decisions that you're going to make. You want to look at the cloud of future possibilities. Now, of course, it doesn't mean that you have to be Bayesian about the parameters necessarily all the time, but again, being Bayesian about the parameters is certainly relevant when you have complex models and relatively small amounts of data. And small amounts of data, as we heard in the great talk on the Netflix recommender setting, could mean a very large data set where you have a small amount of observations per individual. So I think, just to wrap up, there are a few good poster childs now for applications of Bayesian methods. Just off the top of my head, in industry, TrueScale uses Microsoft for ranking games. We saw a lovely talk today on the Netflix recommender using Bayesian methods. We saw another lovely talk on Amazon's demand forecasting. So I'm sort of Microsoft and Netflix, Amazon, what else is left? Uber, okay. Okay, Google, somebody needs to come up with a Google example. But certainly at Uber, a lot of what we do is probabilistic modeling of forecasting things into the future, like a spatiotemporal supply and demand, because that's what we need to be able to optimize the matching of supply and demand. That's sort of a big decision problem. And so that's why we build probabilistic programming frameworks to do that sort of thing within our applications. So more and more nice examples of large-scale Bayesian inference, at least in the industry, and certainly outside of industry, like in the sciences. There are lots of good examples, like Ian's example for astronomy was another very nice one. So there's hope.
Yeah, so I can definitely say in medicine, which is one of the application areas that matter to me, uncertainty is really important, right? So can you imagine having a prediction algorithm where we say, okay, I think you're gonna live if you go into surgery, right? You kind of want to know what the uncertainty is around that before making a decision about whether to actually have the surgery or not, right? So either it's information that needs to be communicated to a physician, right? You have to think of some way in which to communicate uncertainty information to the physician, and then they can make the decision. Or if you think about automating the process, right, and saying, okay, we recommend that you do or you don't have surgery, right, it's probably still information that you want to know and condition on in order to automate that decision-making process. So kind of any way that you go with it, it's really, really important in a medical setting for decision-making in order to have some sense of uncertainty. And I can definitely say, I have a student who, Joe, who worked on using Gaussian processes in order to predict whether or not somebody had sepsis, right? And so, one of the ways you can use the Gaussian process in order to classify somebody as likely to or not to have sepsis is by just feeding in the mean function, right? And another way is to get some sense of uncertainty by, say, like drawing samples from the Gaussian process. And it makes a big difference, even for something as simple as sepsis prediction, just having that sense of uncertainty coming in.
I want to add something. It's not about the question, though. It's I always like to point this out at panels about Bayesian statistics, which I learned from the work of Andrew Gelman, which is that posterior variance. So certainly estimates of uncertainty are very important. They help us in a lot of ways. They help us in active learning. They help us be robust at things. They give us a sense of uncertainty if we're a doctor and we're trying to decide to do something. But just Andrew Gelman teaches me that in the back of your mind, you need to remember when you're looking at these posterior variances that they're just like the posterior expectations, which means that they are conditional on the model being good or good enough for that estimate to be good. And so that posterior variance, even though it looks like something like a confidence interval or something like that, can't necessarily be interpreted that way. It is the posterior uncertainty, meaning if my model was the true model, then yes, this is something like my uncertainty about the thing that I care about that's random, but it's not the same as that because it's conditional on my model being true. And Andrew Gellman also points out in his many papers and books, and also others like Rubin and Meng and Stern and many others, that it's important to check models, and there's this whole world of Bayesian model checking, which is worth looking into. And if you're interested, I'm happy to give you references about that world.
These work.
Yeah, just a small addition. Zubin had some great examples of Bayesian success stories already. Just want to add that for me, what it comes down to when choosing to be Bayesian or not is the structure of the problem. So some of these success stories like rating systems, recommendation systems, these are problems where it's very easy to form a top-down image of how the data is generated. There's something latent, a skill level or a preference, and the data is generated top-down. And in such a case, you can easily write down an inference procedure that gives you an estimate of what you're interested in. In other cases, like image recognition, it's much more natural to reason bottom-up. So you detect edges, you detect your objects, and then something like a neural net is a natural fit. And also the machinery we're developing here that applies to these structures is also useful for many other cases. So, for example, at iClear there was this interesting submission on relational recurrent neural nets, where they basically use the machinery of relational inference, but use it to reason about objects. And yeah, there are many more applications like that, either already out there or waiting to be discovered, I think.
This was a great point by Tim, so I can't resist commenting on it. So there's sort of broadly two kinds of thing that people do in this community, and they're both equally important. They're both really important in some ways. So one of them I characterize as engineering. So we engineer a system that will do some tasks. So we define a task that's like mapping from images to classes, or mapping from English to French, and those tasks can be pretty amazing. And other things I would consider not engineering but science, like getting, modeling a whole system in some way so that we can query it in many different ways and we can gain some understanding of its properties, and we can do experiments on our model and so on and so forth. And certainly we found a lot of incredible engineering successes that don't involve a lot of uncertainty, although I think uncertainty is really important for those engineering tasks as well. But often, as Tim was saying, the Bayesian probabilistic framework is really useful for thinking about the modeling problems. You can sit back and say, well, what's going on? What assumptions do I have? What can I build in? What have I missed, etc. And so that can be quite powerful.
This discussion of engineering reminded me of one of my favorite applications of Bayesian statistics that involves uncertainty. You should all work on it. It's the problem is winning World War II. And basically, in World War II, Jack Good, I.J. Good, and Alan Turing, they broke the Nazi code. And they did it in England in Bletchley Park. And the Nazi code had like two stages. So they would encode, the Nazis, they'd encode a message, and then they'd encode the encoded message to get a double the encoded message. And Turing and Good had two huts where they decoded the first message, where they decoded the first encoded message, and then where they decoded the second encoded message to get the second message. And they used Bayesian statistics, which was not popular in the 40s in England. And it really wasn't. This is not a joke, so Bayesian. Anyway, how does uncertainty come in? Well, imagine they're decoding the encoded message that they got, from listening in on submarines or whatever, and they needed to decide when to send that message to the hut, to the second hut, to get decoded. But they didn't have confirmation. They never would be able to look at the decoded message, which is still in code, and it didn't say, go attack Poland or anything. So so they had to use uncertainty estimates from their model to decide when to send it to the second hut, when they were sure enough about it to send it to the second hut, and the stakes were very high, so, and they won. Yeah.
Thanks for that very timely application. And thanks everyone, that was a great discussion. A couple people have talked about probabilistic programming and tools, and so I want to ask sort of a systems question. So one of the stories about a modeling formalism that's near and dear to my heart that we tell sometimes is you take these simple composable building blocks and you put them together in a way that expresses some kind of intuition about your problem and domain knowledge or whatever. And then once you've done that, then there's a relatively clean, elegant mathematical formalism that tells you how to go from that model and some data to fit whatever about your model it is that you're interested in, make whatever you're interested in, inferences or predictions you're interested in. So there's this nice decoupling of modeling and inference. Everything I just said applies, I would say, entirely to deep learning. Right? You know, it's really very much the same story. The formalism is differentiable functions and automatic differentiation and stochastic gradient. And the deep learning community has seen this really fantastic flowering of applied work and modeling that is really enabled by these systems that are really built on automatic differentiation, you know, kernels, like things like TensorFlow, or going back to Theano, Torch, PyTorch, et cetera, MXNet, CNTK, I'm trying not to forget anybody. And we have fewer of those sorts of tools and sort of less mature, I think we would all agree, less mature versions of such tools in the probabilistic modeling and inference community. And I guess the question that I would like to get people's take on is how much, why is that? Is it just really harder? Or are we just like lazy? Or, you know, I'm pretty sure it's harder because the math seems harder. It's not just sort of like, you know, freshman calculus, but yeah, it wasn't meant to be a joke. Yeah, how much harder, I guess, do you think? And like what if anything can we be doing to sort of close that gap? It's a hard question.
Okay, you guys look to me up. Is this working? Yeah. Right. All right, Dave gets to answer. Yeah, I think it's harder. I mean, integration, approximate or not, is harder. We do have a lot of tools. We have a lot of tools across the whole spectrum where, you know, you can be anywhere from a Bayesian who is basically doing optimization and adds a little term or adds a bit of noise or something, sort of like some of this great work on stochastic gradient, much about dynamics, for example, or even like BIC, which is just optimize and add a penalty at the end, which is super easy and cheap. So you can be everything from that to trying to do like, you know, really, really deep MCMC and you know, exact sampling and things like that. So the problem is probably that there are many, many methods out there, and what's good depends on the application, and so we probably need to develop tools where you can crank a dial and say, this is the trade-off that I want in terms of the amount of time that I can spend. You know, please go do inference. But automating inference tools is a real motivator for probabilistic programming, and we really are behind. We need to provide tools that are easy to run with. But also, I think probabilistic modeling is just generally harder in the sense that just understanding, I mean, I know understanding deep neural nets these days looks like it's really hard, but ultimately at some level you kind of understand what the data is, and you're sort of composing these elements together to achieve some task. Whereas knowing what probabilistic building blocks to put together to model a particular situation is, I think, pretty hard. And it's not actually taught in most machine learning classes. So I think we also have an educational disadvantage there.
Well, I was going to say, I disagree with Matt. I don't think we should declare failure yet. That it's an opportunity. We need to develop these tools, and the work in applied Bayesian modeling has, and especially in approximate inference, has matured where now is a moment where we could think about working on building tools that are robust and usable and flexible, and create I can't recreate your list, but create at least one of those tools for applied Bayesian modeling. I think it's a good problem to work on. Also, just back to the World War II thing, there was a book. I meant to say this at the end, that's actually why I took the microphone. There was a book there's like a technical book about this process, about how they broke the code. I looked it up, I couldn't find the name, but I think it's by Springer. They declassified the original report by Turing and Good, and then some statisticians wrote up the mathematics, and it's beautiful, so check out that book.
Okay, so I could keep asking you guys questions all night, but of course some of you probably have other places to be, and probably there are some people in the audience who want to ask a question, so open it up for minutes.
So one of the things that really spurred the popularity of like some of the deep learning methods is standard benchmarks where there's a clear evaluation metric of success. And this is relatively easy to find in discriminative prediction tasks. Whereas I feel like this is quite hard, or much harder to define in tasks for benchmarking Bayesian inference. So I was wondering if the panelists have any comments or thoughts on how to sort of bring that into sharp focus.
Thank you.
I think these microphones.
They work, but...
Not anymore.
Hello. Testing. It works? Okay.
Yeah. So now Zoom gets to talk.
Oh, okay. Well, I remember trying to set up a class assignment which was like designed like a Kaggle competition, and we could come up with the regression and classification version super easily. But then we thought, how do we do an honest density estimation test? And it was actually quite hard to do that. But I mean, density estimation was one thing you could do, but you just have to make sure people don't cheat by just adding a large number to their log probabilities. It's very hard to detect that. But it is true that it is harder to evaluate, quality of probabilistic models, but it's not that hard. You just hold out data and you see how well you predict it with log probabilities. So it's doable.
So since Zubin mentioned Kaggle, I think I should follow up. So at the start of my PhD, I won a bunch of these competitions. Basically, by taking the recipe, like find the competitions where you have this top-down structure, just implement the inference really well, and then you get great results. And so one example was the chess rating competition, where I used the speed skill model that Zubin mentioned earlier. Another example is one where you're asked to identify the location of dark matter in the universe by its effect on the images we observe here on Earth. And so many problems with that structure actually, their inference is really key to getting the best benchmark results. So I think these benchmarks definitely do exist.
I mean, I could also make a case for, there might be some reminiscing here, but I can definitely make a case for, like, even if they don't, just start them, right? Like, so I remember, like, probably my first paper as a grad student was on looking at hierarchies, right? And it's not something that you really have good evaluation measures for. You have a lot of classification data sets, but if you're going to construct a hierarchy, it's not clear like what the best hierarchy is for that classification data set. So we looked at some of the stuff that Simon was working on with like one of his postdocs, Chue, and different metrics for how you might take a classification set and transform it into something where you could get like a measure or some kind of metric of how well the hierarchy is doing that you were constructing, right? And it's not something that was done a lot at the time, but it's something that people could have follow-on work to, right? Like, so I think UI had a follow-on paper, and he looked at that metric and he was like, well, I don't always like that metric, right? But you started discussion going in terms of like, this is what I've done, this is what I've come up with, this is what I've found, and and let people kind of go from there.
It's true that the scoreboard culture can accelerate progress in terms of building methods, but it's also worth fighting that culture a little bit, to look at a diversity of problems and to let new problems force us to expand our methodology, and for the impact of the method to be that you help solve a real problem, say in science or the social sciences, with the model and with the technique you developed.
So I also find it sometimes amusing that sort of here in the machine learning community, we really like our data-driven forward models that Tim was talking about. But basically the rest of the world, all of the sciences, they do generative modeling. So they actually look at the generative process. There it really matters how you model that. And there's a whole field like Approximate Bayesian Inference that deals with these kinds of things. So I think maybe, and their causality might be very important. So these are all questions that are about generative modeling. And I think there's a huge amount of interesting competitions that we can have there, or metrics to figure out how we can learn these methods.
Thanks. I'll ask another question. So when I was in grad school, we learned all this really great, very special purpose exponential family conjugacy kind of math, and we learned all the here's the table of integrals that we know how to do basically. And it seems like the field has very much sort of moved away from that, which is on balance I think great. Do you? I guess my question is, do you miss that stuff? That's not really my question. My real question is, my real question is, do you think? Well, that's sort of my question. Do you think that there's still a place for that kind of special purpose, kind of exploiting special distributional structure and that sort of thing? Or should we really be just? Do you think these black box methods that have seen all this really incredible development over the last few years are totally good enough? And if not, what are the cases where we can benefit from kind of developing more special purpose stuff?
So I think the nice thing about combining deep learning and probabilistic models is that sort of you can have an outer shell, which is still a graphical model, and then inside you can just look at a conditional distribution P of y given x, and you can stick in there now a much more powerful neural net to model that relationship. And so I think that's actually very exciting. So I don't think we should go back to sort of simple exponential family models, because you can now do these far more complex models. Of course, it's also a function of how much data you have. If you have just very few data, then you have to have few parameters and simple models. But if you have all this wealth of data, then I really think you should stick in the expressibility of the models that we currently have. And we now also know how to deal with them. We know how to backpropagate them. We have the compute power to train all these parameters on these models, and we just get much better models out of it. So I think I'm not longing back to that time. I actually think that combination, the integration with deep learning is very exciting, I think.
That's a challenge though too, right? I also want to fit models where the log density is a neural net, but my understanding is that that's such a powerful approximator that it can be hard for the model the inference method to do anything other than model all of the data with the log density. Like take a mixture model, it will create a neural net that creates a density with the 2 bumps, and then have one mixture component with those 2 bumps rather than 2 mixture components with 1 bump. So this is a challenge. I agree that that's a beautiful, powerful class of models. It's the class of models we want to fit.
So you're talking about that, in terms of the density, they're both equally good, but one is not interpretable. Yeah, so that's an interesting challenge that we can overcome. In fact, there's some work where you basically try to maximize the mutual information between, the latent variables and the data variables itself. And if you maximize that, then again there's a strong coupling, and then the latent variables become much more interpretable again. So I think that's a challenge that can be sort of resolved. Yeah.
That's interesting. I mean, 'cause that's different from it. That's interesting because now it sounds like you've just deviated from the Bayesian activity. Because if the deal is we posit a model, I mean, this is what Matt learned in grad school, I understand. If we posit a model and all inference happens through the posterior, then the posterior itself should do the thing we want it to do. But if we have to specify a different objective function, what is that from the Bayesian perspective?
Right. So this is very interesting, and it goes to maybe a broader question: is how are the models, and we sort of keep designing them, even with elbows and putting Q distributions there that really aren't. Well, we had a fantastic talk, of course, about consistency, but usually you put very strange distributions there, which have nothing to do with the actual distribution that it might converge to, like an MC dropout has a very funny posterior distribution, or we have done dropout variationals that are not even Bayesian, according to Zubin. So, so we play this game, in fact, and so to me that's an intriguing game. And so I'm not religious about that Bayesian thing at all, right? I think it's a tool. It's sort of Bayesian inspired. But we are deviating from that, and we are lacking theory. I totally agree, and sort of we should do more theory on that. But sticking with this kind of dogmatic Bayesian point of view might be actually quite limited.
Yeah, so this actually nicely brings it back to the previous question. I think it was a long time ago now. 2 previous. Well, no, the question about testing and metrics, and because a good way to keep ourselves honest is to have metrics and not be dogmatic about what we do, but actually evaluate honestly on these metrics. And an interesting metric to think about actually is one that I think is inspired by the big lie in machine learning, which is that the test distribution, the test data comes from the same distribution as the training data. And that's a big lie, because that's very nice when we design things in the lab, but when we actually deploy machine learning systems in the real world, the world's a complicated place, and we would be really lucky if we'd actually managed to train it on a perfectly nice distribution that corresponds to what it actually ends up being tested on. So one of the areas where I think Bayesian methods might be very helpful, but also, answering the metric question, is if you do something like take a data set, train your model, whether it's Bayesian or whatever, optimization based, and then evaluate it on a distribution that's somewhat different. And we did some experiments on this just recently in an archive paper where we called it transfer testing. It's just train on MNIST and then test, don't retrain, don't do transfer learning, just test it on other handwritten digits. What happens there? Well, what happens is, you can often get it right, because digits look like digits, but you can also, you can go quite horribly wrong in terms of your confidence. You can be, your systems, your neural net or whatever, convolutional net, can be really confidently wrong in the sense that the entropy over the labels that you get is way, way worse than just answering I don't know, which is probability 1/10 over the 10 classes. So being really overconfidently wrong, which also happens in adversarial examples, is what really worries me if we're going to deploy perception systems, say in self-driving cars or something like that. It's okay to make mistakes, but it's really good to know your limits. It's good to know when you don't know. And that's what I think is really important for these real-world deployments. They're not nice training test splits, basically.
So I guess what I'm going to say, I don't know, I feel like we've maybe confused the topic a little bit, but yeah, no, I totally agree with everything he said, and I think it's really good, and you should listen to what everybody's saying. But yeah, so I think what I have to say is I think that it's all application dependent, right? There are some times where you really care about interpretability, and sometimes where you don't care so much about interpretability. There are some times where you're working with a lot of data and you can do something that's not Bayesian, and your Bayesian posterior is like really peaky anyway, and it really doesn't make that much of a difference. There are other times where you're like, say, dealing with some patient with some really rare disease where you really don't want to do that, or you're dealing with a kind of situation where you're generalizing to new digits or like a new road situation for cars for Uber. And yeah, that's all I really have to say, is that like you need to think about what actual specific application setting you're in and what it is that you care about before making these decisions, and then test them out, right? Like see what kind of decisions have I made, how is that affecting what I'm trying to do.
Great, yeah, that was an in the process of that discussion, some of my other prepared questions were answered, so that's great. One more from the audience, maybe?
Hi, so I wanted to just explore the point that Zubin made a bit more about different distributions that you test on versus training on. So recent progress in variation inference has mostly been in these really flexible parametric models. But what about non-parametrics? Do you think that non-parametrics is actually useful for being more uncertain in regions where you don't observe any data? And should we be trying to get good approximations to non-parametric models which keep the good uncertainty but are computationally similar to parametric models? So I think recently Gaussian processes have made a lot of progress in this. And do you think this is necessary, and do you think this generalizes to other non-parametric models?
There's a mic up there that works, right?
All right. So non-parametrics was definitely one of my passions a few years ago. And then deep learning came, and I thought, deep learning seems, like these models have 100 million parameters. That's infinity as far as I'm concerned. So, that maybe that's a nice way of doing non-parametrics, and maybe that's why they're successful. But of course, they're not Bayesian, so maybe I should do Bayesian deep learning. So it's sort of soul searching. I think it's useful for everybody to know the basic tools of non-parametric models, Bayesian or non-Bayesian. And a lot of machine learning advances have been based around big data scenarios where you really need flexible models. And flexible models also, if you handle the uncertainty well, will generally have big error bars away from where they were trained on. I mean, it's not guaranteed, but it's an interesting thing to explore. So yeah, more flexible models, more uncertainty, more robustness to changes in the data situation.
Yeah. So I'm really excited about this this attempt to combine what we know about Bayesian statistics with what we've discovered recently about deep learning. And I guess I've been given a lot of money by the U.S. government to look into that. So I think everybody's kind of in agreement that this is a problem that's worth exploring, and that deep learning methods have some serious drawbacks that are kind of like really obvious about how to solve and how to approach within a Bayesian statistics paradigm. And the reason I brought up the US funding is because like I can remember like looking at a call and like the call being like, oh, well, deep neural networks have all of these problems, and then they listed off all of the problems that deep neural networks have, and they're all just like trivial to solve within a Bayesian statistical framework, right? So I think you are going to be able to get really far by combining the two.
What agency was that?
It might have 5 letters and start with the D unit.
Okay.
Just to keep things balanced, we should say that there are also great non-Bayesian ways of getting uncertainty estimates. So just having an ensemble of models using bootstrapping your data goes a long way. And when you do use non-parametrics and you make certain choices in order to make things tractable, you also have a particular inductive bias that you're imposing upon your model, and this will also have a strong influence on how you generalize outside of the training distribution. So it's also no magic bullet.
Yeah, I totally agree. I mean, you know, just let's be honest about uncertainty, but there are different frameworks for doing this, and I think it's good to be conscious of it when we do.
So even simpler, if we worry about uncertainty outside of the data, why don't we just model the data with a density model, and then as the probability goes low, we just decrease the uncertainty. We don't have to be patient about that. It seems quite simple.
Great suggestion. No, actually, I think basically anytime we do a discriminative, actually it should be built into the software. Like any discriminative model should also come with an alarm bell that says, whoa, I'm being tested in areas of the input that I wasn't trained on. Actually, I think it should be built into the software.
Isn't that hard?
Well, I mean, it's like anomaly detection, outlier detection, density estimation. I mean, any of those methods could be used. It's just that never just model y given x, have at least some simple, stupid model of x, just so that you can tell whether the model y given x is worth believing or not. Let's do it.
So I can't restrain myself from pointing out one issue with the sort of naive version of that, which is that in high dimensional, if x is high dimensional, then different kinds of x's may have wildly different densities. And so just sort of a threshold that says this is unlikely, you know, like even in like MNIST, 7s are unlikely relative to 1s by that metric, because 1s have much lower entropy. But I just, in good conscience, I have to.
Yeah, but if you stick a picture of a chicken into an MNIST classifier, it should tell you that's neither a 7 nor a 1.
I agree with that. It's our
And it won't. None of the current discriminative methods will do that. That's crazy. There are like 8,000 people at this conference. What's going on?
I mean, so, well, anyway. I'm here for the discussion. So I'll ask one more question, which is, this community has developed and is continuing to develop a wide range of really, really interesting technical tools, mostly in service of, you know, sort of z given x or whatever labels you like, lambda given x, according to this t-shirt.
It's true.
Sorry. Are there other applications besides, you know, applying Bayes' rule that we should be thinking about for this array of really interesting techniques that ultimately, you know, are solving hard integrals or you know, doing other kinds of interesting math tricks? Do you have any sort of favorite examples of that or ideas for what we should be looking at?
I want to answer your question about conjugacy. I've been thinking about it because and maybe someone on the panel will disagree. And the Darwin Annex talk from Netflix was a counterexample to this, but in my experience, discrete latent variables and discrete data, especially high-dimensional discrete data, it's trickier with the variational autoencoder, reparameterization gradient, other continuous latent variable style models. And like we did some work recently, Alison Cheney and Hannah Wallach and I did some work on modeling declassified cables from the State Department that were declassified throughout the 1970s. And you know, it was a big, complicated text analysis model that was designed to detect events, and we really needed the old-fashioned exponential family conjugacy perspective to really scale up that model to analyze 2 million cables to get interpretable latent structure out of it. So, but now we can go back to the other question.
I'd like to reply to that before we...
Oh yeah, good.
Yeah, I agree.
So you mentioned VAEs, and I think one of the cases where Bayesian inference is strongest is if you have a very strong inductive bias or prior that you want to use in order to analyze your data. The problem with conjugacy is that very often we end up imposing an inductive bias that we really don't believe in, just because it makes things tractable. Whereas with a thing like a variational autoencoder, where you have a set of latents and then you have a set of usually convolutional layers that project it into image space, that is actually an inductive bias that is shown to work really well. So last month there was this new paper called Deep Image Prior, where they showed that using this inductive bias alone, you can do amazing things with images. And if you look at things like directed generative models that are tractable, it's not as obvious that those have the same beneficial structure. So I'm actually very happy that we're no longer tied to this conjugacy constraint.
I'm also very happy that we're no longer tied to the conjugacy constraint. Yeah, no, I love that we've expanded out from the class of models of conditionally conjugate.
Does anybody want to answer the question I just asked? I'll repeat it. As a community, we've developed a lot of really interesting sort of mathematical and technical tricks and techniques for dealing with crazy integrals and other interesting kind of math problems. And you know, there's a long history of techniques that were developed to solve one problem turning out to be useful for other problems. And you know, I just think it'd be nice if anybody has sort of thoughts on other applications besides applications of Bayes' rule per se in sort of probabilistic modeling that people should be thinking about, you know, getting more mileage out of the tools they're developing. Or if nobody has any ideas, then we can move on.
Maybe we should think about importing other people's tools into our community. So,
Also not answering the question.
Yeah. So, you know, so I think there's very exciting things like, you know, you can view message passing, you can unroll message passing into an RNN, and then you can view it as an RNN, and then you can meta-learn your inference. So I think that's a very exciting development for this field that hasn't been explored very much, but sort of learning to infer seems to be a tool that comes out of a different community, and that would be cool to introduce here. Now another one is GANs, although you would argue that's being produced in our community. I don't know whether that falls inside or outside our community. But you know, that's another interesting tool that's being developed that could be applied and mixed with things that we do in this community.
Yes, I actually do think that the machinery we're developing here, Bayesian inference and how to actually approximate it in practice, is going to be very useful to answer many of the questions we have in AI. So in AI, we want to reason about things. And really the best framework we have for understanding what reasoning is, I think, is Bayesian inference still. So if you look at Jane's book, he starts out his book with this great anecdote of driving past a street where a glass window of a store is broken, and the question is like, okay, what is the inference we should draw here? Like, did someone break in, or did someone forget their keys and this was just like the most practical way of getting into the ruined store? And then this reasoning problem we solve using approximate Bayesian inference in practice. And I think these tools and this machinery can be embedded in more general neural nets, and it will guide the way we structure our neural nets in order to solve these difficult inference problems.
So I think I'm going to try to answer your question, but tell me if I'm wrong. So, of course, lots of interesting things in science and AI and engineering and so on can be posed from a Bayesian inference point of view. But the tools that we're developing, if we think abstractly as, rather than developing optimization tools, we're developing approximate integration tools. So where else does integration help out there? And I'm not an expert. I don't know, but obviously there are many fields of science and engineering that involve computing integrals of things. Like there are a lot of counting problems in theoretical computer science. Counting problems are problems that we could throw our machine learning approximate Bayesian inference machinery to solve. And I'm pretty sure that in physics there are a lot of problems that involve computing important integrals that tell us something about the physical world or constants of the universe. And some of the same tools could be used. We could export rather than import. We've imported a lot from physics, including some really smart people sitting here. But we could export some things as well to those communities.
Okay, we're going to do one more question from the audience, and then people can get dinner or whatever it is we're people do.
All right, thanks for letting me have the last question. I was actually going to ask this of the Bayesian deep learning panel tomorrow, but why not ask you guys as well? And I think Max knows what the question is going to be. So I was in the meta-learning conference yesterday with Jürgen Schmidhuber, and he's saying, okay, we're going to have a universal learning algorithm that will learn everything that needs to learn about the world to act intelligently, right? And we know that Bayesian decision theory tells us that probability theory is the foundation of rational decision making and is optimal. So the question of the panel is, if we just have unlimited compute, we have these agents playing in simulated environments for as long as they want, will they discover Bayes' rule and decision theory? And if they do, how do we know they've done it? And if they can't discover it on their own just by using LSTMs or whatever, do we need to engineer it in by hand, or can we just let neural nets just do everything, and we never need to write down P of X anymore?
I think that's a really excellent question. To rephrase the question is, if you have basically a reinforcement learning system, do you ever need to write down probability theory in it? Because it should discover probabilities if that is the thing that it needs in order to collect its rewards. And so this is a question of, how much data do you have? If you have an infinite amount of data, then possibly that could work. But even humans growing up don't have that much data, and I think it's very, very useful to know sort of the elementary math building blocks that you could use. So it's basically a super useful elementary prior that you could use. But I think philosophically, I think it should be possible. It's a really fun experiment to run, I would say. Probably only Google can run that experiment.
I agree with Max. Another thought experiment would be, we know certain things like the laws of gravitation or the laws of optics and so on. And, we could, in theory, learn about the laws of gravitation by throwing a gigantic neural net and a gigantic simulation of like planets moving around and have it learn that, but that just seems crazy. So if we know that these tools are important for rational decision-making agents, then let's combine them with flexible functions. Let's not just say we're going to simulate lots of data and learn it. But I think in principle, sure, yeah, if you have enough data and enough compute, and that might be the argument for, like, it's just a question of levels of explanation as well. Like, people who study neuroscience and cognitive science, sometimes they use ideas from Bayesian inference to look at human and animal behavior, but is it like Bayes' rule is actually implemented in the brain? At what level? Is it sort of approximated? Is it just some funny thing that's happened through evolution and lots of like learning that kind of approximates Bayes' rule? So it's sort of levels of explanation, I think.
I just wanted to say, it's very interesting. If you look at the behavioral psychology literature, there are papers claiming that what the human brain is basically a Bayesian inference machine, and then you have these great examples showing how we are amazing at intuitive Bayesian inference. And then in the same community, there are also papers being written where you have different experiments showing we are terrible at drawing Bayesian inferences and as intuitive statisticians. So I think the answer will be that if you do meta-learning and you learn your agent that way, that just like humans will be great at doing Bayesian inference in some cases and very terrible at it in other cases.
So I was going to make some snarky comment about how I'm going to stop doing research and just let Google run its computers on a lot of deep learning and do a lot of deep neural network learning. I think that more seriously, we're always in a situation where we have a limited number of data about certain things, right? So no matter how many people there are on Earth, right, there's going to be some like really, really rare disease that like only 5 people have, right? And in these settings, we're not actually living in a world in which we have an infinite amount of data that we can generalize off of, and so this kind of Bayesian inference or Bayesian statistics is always going to be useful in those settings.
All right, we're a little bit over time, and I don't want to impose too much on our fantastic panelists or our fantastic audience, but this was great. I learned a lot. I think we should all thank our panelists, please.